Hi, I am Pieter Abbeel. I'm a professor at UC Berkeley and co-founder of Covariant. At Berkeley, I work on AI and robotics research and teaching. At Covariant, we bring AI robotics into the real world. Now, here in this session, what I'd like to share with you is some of my thoughts on how we can get to a more general solution for robotics. What are some of the challenges, some of the progress that's being made, and some of the opportunities for you to work on. Now, one of the videos that's inspired me for the past 10 years and counting is this video over here. I really like this video because when you watch this, what you see is effectively the dream many of us have had for many, many years, which is a robot in the home doing many of the chores we wish robots would be doing for us. But of course, there is a catch. And the catch is that this robot is being teleoperated by one of the students who built the robot. And so every single motion is really puppeteered by the student. But what it shows is that the hardware is capable. What we really need is better software, the AI, to make this robot smart enough to do these things on its own. Now, when you think about robots today, where they actually are, it tends to be in factories, building cars, electronics, and so forth. And so what we're really after here now is to see if we can get robots in more open-ended environments. Now, when we think about AI systems in general in open-ended environments or solving problems that go beyond maybe the exact thing they've been trained for, a great example in computer vision, of course, is the practice of pre-training on ImageNet and then fine-tuning on other tasks. That works really, really well, and the pre-training happens on something that is not exactly where you're going to be using your neural network later. What we've seen is even in a bigger way play out, of course, is natural language processing, where pre-training on text from the internet, as we saw with GPT and BERT-like models, can lead to a very, very powerful pre-trained model that can then be fine-tuned or even just probed to solve other tasks. Now, how about robotics? Wouldn't it be nice if we had something similar, a very large pre-trained network that we could then reuse and maybe reuse in different homes, a little bit of fine-tuning, and it would just work there? Well, it's a big question mark today what that is. There is no such common practice in robotics research where there's a specific pre-training on which then is built to do a more specific task. The closest there is probably that, well, robotics is often vision-based and that a lot of pre-training on ImageNet happens, but that's not really what we need. We need much more than just vision. We need a vision and control system together, and it's not really clear where we're going to get that. That said, what I'd like to do in this session is to share my thoughts on maybe how we could get there. Don't think of this as a kind of ground truth. This is for sure how we're going to get there. It's more one possible route, and I definitely invite comments, email me suggestions. Very curious what your thoughts are, but let's take a stab at it and see where we can start from at least. So what we want is ultimately a very large robot brain that is ready to either directly do new things or be quickly trained to do new things. Now, one natural thing you might think, and I agree, is, well, let's pre-train on a lot of internet video. This would be some kind of unsupervised learning because we don't have to explicitly provide labels, and we could train a network that maybe can do video prediction or related tasks. In fact, if you want to stay purely in computer vision yet contribute to robotics in a very fundamental way, I think this might be the best thing to be working on. Much better video prediction will likely lead to a big part of what we need here. One thing I want to highlight, though, is that it doesn't need to be just video. It can also be text or a combination of text and video, because very often when we think about skills, we might write them up in text. There might be a recipe for a robot to cook something that's written in text rather than a video showcasing exactly how it's done. And so that might become equally important as we get to higher levels of abstractions for our robots. But now, of course, just visual and maybe textual representation learning is not going to be enough. The robot will have to know something about its own body, how it can achieve things in the world. And from just watching internet videos, that connection is not very directly made. So we need some real world or maybe simulator experience for the robot. And what can we do with that? When we have access to that, of course, the real world tends to be more expensive. mostly we probably want to rely on simulation if we can. We could maybe have the robot do some multitask reinforcement learning. But then, of course, you have to specify the tasks. It's nice to be multitask in general, but specifying tasks is tedious, writing out reward functions, setting up the simulated environments, and so forth. So what else can we do? Well, maybe they can, in an unsupervised way, pre-train themselves, running some kind of RL against an unsupervised objective. And we'll dive more into what that might mean. But the real important point here is that we wouldn't have to provide reward functions for everything we want the robot to train itself for. Now, with these two in place, we might start getting somewhere. But what we don't have yet here in the picture is how humans are going to play a role in this. And naturally, we would want humans to somehow influence the results of what the robot is learning. So we want some maybe human-in-the-loop reinforcement learning as part of the picture. And of course, as we bring in humans, humans can also provide demonstrations. And there's demonstration data often already available in various data sets. So you probably want to bring in demonstrations too. These demonstrations could be used for direct imitation. That's certainly a viable route, but that's a bit specialized. If we think about a more general large neural network as the kind of foundation for a robot brain, then maybe the better way to use the demonstrations is to see if we can use them for a few-shot imitation learning. And so here's the picture that's currently, at least in my mind, of the pieces we need to make come together, or we could make come together to make this all work. By no means am I saying this is the only way. There might be other ways, but I do think this is going to be a pretty powerful way to get towards a large neural network that can be very general, and maybe as general as we need to bring robots into a wide range of environments, many different homes, offices, and so forth. But of course, each of these red bubbles corresponds to areas where we still have to make a lot of progress to make this a reality. So in the rest of this presentation, I want to share with you some progress that's already been made on those 5 areas, as well as remaining challenges and opportunities for future work. First, I'd like to share with you some of the progress in unsupervised learning and reinforced learning brought together. And what I'm going to present, this is going to be in single task reinforcement learning, but big picture wise, certainly I think it's going to have to be multitask and complemented with unsupervised and so forth. But for now, the main progress that's been showcased has been in combining unsupervised with single task RL. So let's take a look at that. So the question here is, can we do reinforced learning from pixels in an efficient way? And if you ask this question about a year and a half, 2 years ago, probably the most kind of indicative plot of where the field was at is shown here. So what you see here is 2 learning curves. So higher is better, more reward. And off to the right means that it took longer, this number of steps the agent took during the learning. And so what we see here is that the blue learning curve shoots up much faster, is a better one than the green ones. What's the difference? And this is in DeepMind Control Suite simulated robotics environments. So the green ones versus the blue ones, the blue one has access to the underlying state of the environment. This could be coordinates of objects of the robot and so forth, velocities of these objects and so forth. The green one only has access to pixels, so a camera view of the environment. And what we see is that learning with only access to pixels is not as fast as when we have access to the underlying state. And maybe this isn't too surprising, because the whole notion of state is that it's the most succinct representation of the configuration of the world. And so learning with access to that likely is going to be faster. But there's a question you could ask here, which is, well, does it really have to be faster? Because if the state is information-wise available in the images, then maybe learning could be as fast from images. Maybe we can bridge that gap that here is 100x in learning speed. Maybe we can bridge that gap if somehow we're more smart about how we extract things from these images. Of course, this might remind you of the famous cake by Jan LeCun, where Jan in the NeurIPS opening keynote in 2016 told us about, well, reinforced learning is great, it's the cherry on the cake. We all want the cherry on the cake, of course. But the foundation of the cake, the majority of the mass here, is unsupervised learning, because that's where we have a lot of data that we can use for learning, whereas reinforced learning sparse rewards, not as much signal available. And of course, in the analogy, the icing on the cake was the supervised learning. So can we effectively have a le cake version of RL is another way to think of the question. So, well, what is the most effective? Well, let's take a look at unsupervised learning for visual inputs. Contrastive learning has made tremendous strides and kind of put unsupervised learning really on the map in vision, similar to how it's been on the map in NLP for several years now. And one of the first breakthrough papers was the Contrastive Predictive Coding, CPC v2, which has a plot here showing that consistently having also unsupervised learning helps you outperform only having supervised learning. This is on ImageNet. Of course, since then, there's been a lot of improvements. Perhaps most famously so the breakthroughs through SimCLR and MoCo. What do SimCLR and MoCo do? Well, you download images from the internet, let's say, or from your unlabeled data set. Now, it's unlabeled, so you don't know what's in the images. Of course, we know these are a dog and a cat, but we're not going to label. We don't want to put in that effort, so it's just 2 images. Likely they're images of different things because they're just randomly 2 images downloaded from the internet. Then for each image, a duplicate is generated, but not an exact duplicate. It's actually duplicated with maybe a grayscale operation or a flipping and cropping and so forth. Then a neural network is supposed to process each of these images individually, generate embedding vectors that are 3D objective attracted to each other when they come from the same original and repelled from each other when they come from different originals. So that's the idea. In some sense, fairly straightforward, but of course, getting the details right is what made it all succeed. Now, we can do the same thing in RL. In reinforcement learning, we have our agent collect data. That data goes into a replay buffer. We can grab data from that replay buffer, in this case, a stack of frames. Why a stack of frame rather than a single frame? Because velocities matter in robotic control. And with a stack of frames, we can effectively infer velocities if we want to do control. Now, then this stack of frames gets encoded. And if we just did regular RL, it would just go through the top pipeline to an actor network and a critic network that would be trained with the reinforcement learning loss. But in this case, we're going to, in addition, feed the output of the encoder into a contrastive learning loss, where we do exactly what I described when describing SimCLR and MoCo. We will sample other stacks of frames from the replay buffer. Those will be negatives, and we'll then have this be repelled from those others, but close to augmentations of itself. Okay, so the way we do augmentations here is by random cropping. We tried many different things. Random cropping was most effective. Then in the contrastive loss shown at the bottom here, there's this weighted inner product possibly. We found that indeed learning the weighting of the inner product actually helps in our experiments. So we're weighting the inner product. And then the other thing is that we use a momentum encoder, which is the MoCo version of contrastive learning, which again, experimentally we determined is quite helpful. In red, uses the exponentially moving average. In blue, it doesn't. Okay, so once we put this all together, here's what we get. Here are 16 learning curves. In each of these plots, we have a simulated robotic environment where in gray, we see the learning curve when we give access to the underlying state. In red, the learning curve when we only have access to pixels, images of the environment. What we see is that the red learning curves almost consistently match up with the gray learning curves. And that's amazing, because what that means is that thanks to including the contrastive loss into the reinforcement learning process, we're able to be almost as efficient when learning from pixels as when learning with direct access to the underlying state. Now, of course, these experiments are in simulation, and we can do the direct comparison here, but even more important is that once we were to transition to real world, and I'll show some results later, we typically do not have access to the underlying state. And so the gray learning curve is simply not available. All we could have is the red one, and if the red can match up with the gray, then we learn fast, even in the real world. Here's a comparison with past approaches. You might think efficient learning. Maybe we should do model-based RL. What I showed in a previous slide is soft actor critic combined with contrastive learning. Well, we compare with model-based RL, and we see that we can do as well or better then model-based RL on these vision-based robotic control tasks. And we have a comparison here with Planet for the model-based method, but also then with other model-free methods that do vision-based RL from the past. And we see that curl in red consistently outperforms them, and matching almost with gray, which is learning directly from state. Okay, so here is another comparison in a bar graph. On the left, state-based soft actor critic. Next to it, curl. And we see with 500K steps, it pretty much matches up. 100K, it's still a bit better to have access to state. And then previous state-of-the-art methods going off to the right, and curl consistently outperforms them. We did a similar comparison in Atari. On the left is a table with the scores in each of the games after 100,000 steps. This is the Atari 100K benchmark, which tests how fast you are learning, focused on a very small number of samples. And we see that we, with curl, do kind of split the wins with simple, which is a state-of-the-art model-based method, outperform rainbow, which is the method we build on top of by adding the contrastive learning to it. On the right, you're looking at the human normalized scores across all games. Curl outperforms efficient, rainbow outperforms simple. Now, one thing you might have seen in the robotic control suite of tests is that in a few cases, there was still a gap between learning from state in gray and learning from pixels in red. So we dug a little deeper to try to find out when is it that there is still that gap, and why might that be? And so what we found is that, at least our hypothesis was that it's because maybe there are some state variables that cannot be extracted from the images, like contact forces. And so what we looked at is the underlying state and set up a supervised learning problem from image frame stacks onto underlying state, and trained for a long time, very large network, to see if we can indeed consistently extract the state from the stack of images, or if we cannot. And what we found is that when there's a gap, that tended to correspond to situations where the underlying state could not be fully recovered from images, suggesting, well, maybe if we were to do this in the real world, we might maybe have to equip our robot with a contact force sensor to get the exact same performance as we can get with access to full state information. Okay, now, one question you might have is, can curl learn representations without reward? Meaning, instead of having a network with two branches, one for the reinforcement learning loss, another one for the contrastive loss, and everything backpropagating all the way, can we have the encoder part of the network only be trained with the contrastive loss and not with the reinforcement learning loss? In these experiments, we saw that often we can, but not always. In work we've done since, we found that we can make this actually match up, it seems, if we use a temporal contrastive loss rather than an instantaneous contrastive loss. Now, from there, we started to think, can we now put this on a real robot, and how efficient might it be? So now, reinforcement learning in the real world, if you learn from scratch, is going to take a long time. It's a bit ineffective, as anybody who has tried probably knows. So we start with 10 demonstrations. It takes about 10 minutes. Tell your Pieter robot to do a task, maybe pick and place something, push a block, and so forth. Put that data in the replay buffer. Then we do contrastive pre-training on that data. So we pre-train the encoder. And then we do reinforcement learning, trial and error learning, for about 30 minutes, where we also use data augmentation. And that's it. So about a total of a little more than 30 minutes, where only the first 10 minutes really require the human to do something, and then it learns on its own. What can it do for us? Well, here's one example. So what we see here is on the left, an example demonstration. This is a pull task. So we demonstrate as one of our 10 demonstrations. Then, after the unsupervised learning, followed by reinforcement learning, 5 episodes of reinforcement learning, which is about 5 minutes in, it's already capable of doing some kind of pulling. It's a first success. After 45 episodes, about 30 minutes of reinforcement learning, it's able to achieve pretty much an optimal policy, which when we evaluate has 28 out of 30 success, which we're watching here. Now, with I showed this for pull. We did this for many tasks: reach, pick up, move, pull, light switch, and drawer open, all in the real world. And each of them, the experiment took less than an hour. And we use the same hyperparameters across all tasks. In the table below, you can see when the first success happened, when it started being optimal/converged, which is actually relatively fast, 15, 26, 46, 29, 16, 20 minutes, at which point it has a certain success rate, which in 4 out of 6 is 100% success rate, and in 2 of them, which are a bit harder, still above 85% success rate. In just about roughly a half hour of effort to teach a robot a new task. Now, I highlighted 2 works here, curl and then firm, but there's a lot of related work happening in this space, and I'm highlighting it on this slide here. I can't step through all of it in the time we have for this talk, but there's a lot more work happening in this space, and there's a lot more work that can be done in this space. A very exciting area. There is some work that uses auto-encoded representations rather than contrastive learning. There's some work that shows that just augmentation can go a very long way. There's some work that shows you can actually decouple representation learning from RL with augmented temporal contrast. And then, of course, there's work looking at applying to real robots. And there's other work happening that's not even listed on this slide. But I'm sure you'll find it as you start reading these papers. So what we covered so far is how it can bring together unsupervised representation learning with reinforcement learning. But now if you think about it, this is not really fully unsupervised reinforcement learning, because the agent is not unsupervised collecting the data. We still had reward functions in all the results I showed you. But if we really want our agent to independently be able to collect a lot of data, learn on its own, we needed to somehow do that without us specifying a reward for every possible task. And so that's what unsupervised pre-training in RL is concerned with, pre-training the agent with the skills to do a wide range of things, maybe not all things that we want, but then hopefully that makes the agent ready to do what we want quickly later. Now, there's quite a bit of work happening in this space. And what I want to share with you here is kind of a little bit more detail on one specific direction that I'm personally really excited about. And this is the kind of unsupervised pre-training through an intrinsic reward in the form of state visitation distribution entropy. So when our agent is just acting in the world, states are being visited. We can then measure the distribution of that empirical, the entropy of that empirical distribution over states. And think of that when it's high entropy, it means our agent visits many different states. It's a very exploratory approach from our agent, and it can learn a lot. Whereas if it's a very peak distribution, very low entropy distribution, then it's probably not learning a lot. So we're still going to, in some sense, specify a reward function, but this reward function is very generic. It's not related to a task. It's this one reward function that can be applied anywhere, which is entropy of the state visitation distribution. Now, to be clear, I'm saying state, but ultimately we're going to have access to images, and so there's going to be some entropy over the distribution over images, not over state. There's no assumption here we have access to state, even if some of the earlier work assumed access to state. Certainly, if you have access to state, the idea remains valid, but ultimately we want to do it from images, of course. So now the problem is that measuring state entropy is intractable in terms of compute in most settings. So how are we going to do that? Turns out there's this approximation based on k nearest neighbors, in that when you measure the log probability, which is the key term in computing entropy, rather than having access directly to some probability distribution value, you could use the distance to the k nearest neighbor. And that distance can be used in what is called a particle-based estimate of the entropy. And so in our case, we'll look at the k nearest neighbor of a state, or an image possibly, and then see how far that k nearest neighbor is, and that will then help us estimate the entropy once we cycle over all the data. Okay, so what does it look like? When we do this kind of training, active pre-training, observations will come into the agent. There will be a neural net encoder that turns this into a representation. Now, to make sure that's a good representation, and as we saw before, contrastive learning can definitely help reinforcement learning. We're going to have this contrastive loss again here on the right and up to make sure we get good representations. And then For our reinforcement learning agent, the reinforcement learning loss will be based on the entropy. The reward is the entropy achieved according to that k nearest neighbor entropy in a trajectory. And so that's going here straight up. So at this point, we effectively have a similar agent in terms of implementation as what we had before with curl. The difference is now that instead of having a task reward on the reinforcement learning branch, we have this particle-based entropy that we use as a reward. What we use to measure this particle-based entropy, we look in the replay buffer, and everything that's in the replay buffer is used to compute the k nearest neighbor to the states encountered. And so when you have a trajectory that's very different from what's already in the replay buffer, it's going to have a very high entropy, a high score, high reward. Whereas if you have a trajectory that has very close proximity to states already in the replay buffer, well, then you'll have a low reward and you'll be discouraged to have that kind of trajectory again in the future. Okay, that's what we do for pre-training. No task reward is needed. And here are some learning curves. So in green is our approach. In red is when you run with a count-based bonus, and in blue is you run from scratch. Dr. Q is the approach we build upon, but we do pre-training. The pre-training is accounted for in the horizontal axis here. And so when we look at the efficiency here, we see that across a range of DeepMind control suite environments, first spending time on pre-training before training on the task is actually beneficial very consistently. And in some tasks, the more sparse reward tasks, the second half of tasks, it's absolutely critical to do this kind of pre-training, or you barely learn anything at all. We also looked at this in the context of Atari. So APT is ours, active pre-training. Then there are some other prior works on pre-training. Visor's a pre-training work. And then SPR, Dr. Q, curl are representation learning approaches, but they don't do the active pre-training. And what we see here is that APT is strongest in about half of the games, better than any of the other approaches. So this active pre-training really helps compared to not doing active pre-training. Then one thing you might wonder is if we compute our entropy based on what's in the replay buffer, well, isn't there a lot of redundancy in the replay buffer? Can we do something more clever to effectively keep a longer horizon of information around? And indeed, there's some recent work out of NYU, Dennis Yaretz and collaborators. They show that if you can do that, you can actually do clustering on the members of the replay buffer and then use a particle-based entropy using the clusters rather than all the original data. And this can, again, give you a bump up compared to what I just presented. What you see in these learning curves here, this new approach called Proto-RL in red, yet doing better. Again, pre-training, roughly same approach, but has this cluster approach. Then you might wonder, well, it's great to pre-train for maximizing entropy, because that means you see a lot of things and you bring variety in your replay buffer and so forth. But how about this notion of skill, something where you can just index into it? You say, hey, I'm going to maybe execute skill 1 now or skill 2. Well, there's a lot of work actually that goes in that direction, listing some of the work here. Variational intrinsic control, Diane, Valor, Visor, they all go in that direction. And what's under the hood there? Under the hood, they all optimize up to some details of variation between the approaches, but ultimately they all come back to this main idea. You're going to optimize the mutual information between a latent variable z, which you sample at the beginning of your trajectory. So it effectively indexes into your skill that you're about to execute, and you feed that into your policy, that latent variable z. And then the state sequence that ensues from that. And what is mutual information? Well, it's entropy of one variable minus entropy of that variable conditioned on the other variable. And so they optimize h of z, the latent, minus h of z given the trajectory. What does that mean in practice? Z is a latent sample at the beginning of the trajectory. Maximize the entropy of z means you sample, for example, from a Gaussian or a uniform distribution. And that's all you have to do. Then the second term, what it means is that you will want to be able to, from the trajectory, be able to successfully predict what the latent was that you used when generating that trajectory. So this approach is learning a classifier from S to Z. It's actually very interesting because you get a wide range of skills that you can index into. But one thing that happens, at least in our observation, is that it doesn't explore as well as the entropy-based approach I just described. It doesn't get as good coverage. Now, One way to actually combine these ideas is to, when you think about mutual information, you can also optimize the entropy of S minus S given Z. That's just the other way of expressing mutual information. Once you do that, well, entropy of S, that's what we've been talking about all along. That's the particle-based entropy that we used that's doing exactly that. And then we just need to add this additional term of effectively being able to predict S from Z, which is a classifier in the opposite direction. And so there's a bunch of work going in this direction. I'll show you some results momentarily, but while we have both approaches on here, what's the difference? The difference is that here you have a direct encouragement of maximizing state entropy, which is really aiding exploration, while still ensuring that you can index into skills by requiring this entropy to be low, that is making S predictable from Z. Of course, you could say, aren't they both the same mutual information? Well, this is one of those cases where the devil's in the details of how the signal propagates and so forth, and it seems that this second decomposition of mutual information might be more helpful in terms of encouraging wider exploration. So if we apply this idea, we'll call it APS, APT, which I described earlier, but then with also this extra term, and here's the results on Atari. We see APS is winning more than any other approach, comparing with APT, which does not have that extra term, Visor, which has the kind of reverse mutual information, then some representational learning approaches, model-based. So pretty extensive comparison. This is really helpful. Now, if you're curious about this general line of work, I have a list of references here. On the left is effectively the references covering what I discussed. And then on the right and top, I'm saying, well, there's also other related work on exploration bonuses, curiosity, surprise, VIME, and so forth. So a lot of things you can go read up on. And I think a lot of things still to be discovered, because even now, I wouldn't say these exploration methods are truly what we would hope for in skill acquisition or pre-training. There's a lot of room for improvement still. Now let's take a look at how and why we might want to bring the human in the loop during the learning process. So, in reinforcement learning, one of the big challenges when your system is interacting with the world and trying to optimize reward is to make sure you design a suitable reward, a reward that you actually want optimized. Now, here's an example. Optimized policy in this simulated robotic environment, right? Optimized, going as far as possible in the X direction, minimizing torques squared, keeping the center of mass at a certain height. But what we see is a very unnatural behavior. And so maybe this is not what we want when we have a simulated character. So now we have to go change that reward function and somehow help it become reflective of what we want more closely. That's always hard to do. This is just a simple simulated robot that we want to run. But imagine you're trying to do this for cooking. What could happen as the system optimizes your reward function? If it's a little bit misspecified, a lot of things can go wrong easily. And even in things like games, which are relatively simple in many ways, it's just a boat racing game, because there was a reward to hit some obstacles. Well, it turns out that this boat is not participating in the race anymore. It's optimizing the score by just circling around in the harbor. So this is very, very interesting that even for a simple thing like games, even though ultimately we want to go to the real world where it's even more complex, it's already hard in games to get this right. So what's an alternative solution? Well, let's think about it. This is the standard reinforcement learning process, which we've figured out how to make work reasonably well. So we might want to stay close to it if possible, but it has this reward input where we need to somehow write a piece of code that measures reward and gives it to the agent. What if instead we put a human in the loop? Now, simplest way of putting human in the loop, you might say, is just human watches and maybe pushes some buttons to say, oh, this much reward, that much reward, and so forth. That's a bit hard. It's hard to constantly watch the robot or whatever agent you have and constantly be giving rewards. So if we want to bring the human in, we probably want to do something lighter weight than constantly watching. But here's something we can do actually that's very effective, as I'll show you. Instead of having the human constantly watching, constantly decide how much reward, we present the human with short clips of past executions, pairs of clips. The human watches both of those and decides which one they prefer. Or there could be a tie. We're building on some prior work here, of course, listed on the slide. So what does the full framework look like? In step 1, the agent collects samples via interacting with the environment. Step 2, we present some clips to the human, who then says which one they prefer over which other one. Then we learn a reward function from those human preferences. How do we do that? We use the Bradley-Terry model to model the human preferences, which says that the probability a human prefers a clip sigma 1 over a clip sigma 0 corresponds to exponentiated reward along clip sigma 1 divided by exponentiated reward along sigma 1 plus along sigma 0. So it's a standard softmax model, and this reward here is going to be a neural network. We're going to train a neural network to predict reward that is consistent with how the human is given preferences feedback. So then after we have learned that reward function, we optimize the policy using an off-policy algorithm. We use soft actor critic. Are we done? No, because this is just some initial signal based on initial trajectories, what the reward function could be. We optimize against that, but now we need to loop around, collect more interactions with the environment, get an update on the human preferences, because we now have explored a different part of the space probably, update our reward function based on that, update our policy again, and repeat. Okay, now to make this practical for a human, you don't want to present them with some random walk, jittery behavior in the beginning that takes a long time to make sense of. So instead of presenting the jittery behavior on the left, which is how an agent would start out without pre-training, we're going to use the active pre-training that we talked about earlier. So even before the human is in the loop, the agent discovers some interesting behaviors. And so the clips from the get-go are going to be more interesting and easier for a human to decide which one they prefer over which other one. So can a human teach novel behaviors this way? Turns out, yes. The test we ran here is we gave a human 2 different tasks. Task 1, make this card pole swing counterclockwise. Task 2, make it swing clockwise. And we see that indeed, through this process, human in 2 different runs was able to teach what they want and have it execute on the task. Here's another task. Again, 2 different runs. Lift the front left leg, lift the front right leg. And we see that in just 200 queries, less than 30 minutes of time, the robot acquires these 2 different skills depending on what kind of feedback the human is providing. So the human is really controlling the outcome here. Human can teach in 50 queries backflipping. So this is a hard task to specify a reward for, but through this preference-based learning can be taught relatively quickly. Another question you might have is, can we avoid reward exploitation where the wrong reward gets optimized? Well, let's think back about the running. There's a 2D version of the running, and we see that when fully trained, it's dragging its leg. That's with the standard DeepMind control suite reward function. Sure, it's moving forward, but it's not the kind of running we probably were hoping for. Now, what we see on the right here is after training with human preferences, the human is able to teach it to run using both legs and something that is what we would call running rather than dragging. Now, to set up a benchmark for all this to make it easier to compare, rather than having an actual human in the loop, we set up a scripted human, which will look at the reward, underlying reward, related to, let's say, DeepMind control suite's underlying reward function, use that to then output preferences by comparing the reward along 2 trajectories. And of course, you can have different versions of this human. You can have a noisy human that is not exactly comparing, but might use that Bradley-Terry model, the softmax model, or one that just randomly flips bits and so forth. And that benchmark will be released really, really soon, hoping that some of you will take advantage of that and contribute to improved human-in-the-loop reinforcement learning. So this way we can evaluate the agent quantitatively by measuring the true average return. So what we get here is a comparison on quadruped, cheetah, and walker. So in red is the learning curve with soft actor critic, where we have access to the underlying DeepMind control suite reward function. So that's as good as it's going to get, is the oracle. And then in green, yellow, and kind of dirty green, we see 3 learning curves for our approach with varying amounts of human input. Green is the most human feedback, and the dirty green has the least human feedback. And we see that indeed it can start getting close to the oracle performance. It's a comparison here with a method called preference PPO, which is from Cristiano et al., which uses PPO, which is a on-policy RL algorithm rather than SAC, which is off-policy. The other difference is that in our approach, we have the active pre-training instead of directly bringing in the human, and we see a much more effective training with Pebble, which is our approach. So if you're curious to dive deeper in any of these methods, or more generally this field of human-in-the-loop reinforcement learning, here are a few references that might be good starting points, and you can probably work your way from there pretty effectively. Now, the remaining component is using demonstrations, and as I alluded to, I think the most kind of generalized way to use them is to use them in a few-shot imitation learning framework. I don't have the time in this presentation to get into a lot of detail here, but I do want to provide you with some of the references of the work there. Probably the first work to look at would be the one-shot imitation by Duan et al., which introduced, actually before a transformer paper existed, introduced multi-headed self-attention in the context of few-shot imitation learning with a lot of the things that you are all familiar with today. But in this case, it's paying attention to a past demonstration to decide what to do now in the current situation. And it turned out quite powerful for different kinds of block stacking tasks. Then there's a visual version, of course, that you might want to consider. This original paper was based on access to state. I'm listing two vision-based versions at the bottom. The last one is actually very similar to the original one-shot imitation, but vision-based input and uses kind of the modern transformer framework for multi-headed self-attention rather than the in parallel invented version of this in the original paper. Now, when I zoom out for a moment, even though there's been a good amount of progress in this field, I would say the big missing piece is that when you look at the tasks being solved, they are in a restricted domain typically. For example, few-shot imitation for block stacking, or few-shot imitation for moving objects from one bin into one of a set of cubby holes. And so the generalization there is, from one demonstration, do you know which object to pick and which one goes into which cubbyhole? But during training, you're already training on moving objects into the same cubbyholes. So there's a limited generalization for now in the works happening. And I think doing this across domains is a big open challenge that would be very exciting to see progress on. Okay, so this is the full picture and a summary of what we've covered so far. Now, one thing you might wonder is this large neural net brain that sits in the middle, what is it going to look like? Because don't we usually have slightly different architectures for few-shot learning versus unsupervised representation learning versus human-in-the-loop RL and so forth? And the answer is yes. So far, we often have some somewhat different architectures. And so we're going to have to unify this. And what I want to share in the last part here is some of my optimism about the fact that I think we will be able to unify this. We, meaning not just me, but anybody in the community working on this, we have a good shot at unifying this. Probably the most general model we've seen so far in the community is in language modeling, where models can be trained to, from text on the internet to complete articles from just a prompt. And here's an example of that. And the article, when you read it, actually fairly realistic text. Might not correspond to reality, but the text reads realistic. It reads so realistic, actually, that time when this was released by OpenAI, there was this whole thing about, oh, wow, this model might be too dangerous to release in the wild. The text is too real and so forth. A lot can be said about that, but what we want to talk about here is actually the other part of what happened in that release, which is when you looked at a table of results, it showed that a single language model trained on a lot of text on the internet, then fine-tuned for every row corresponds to a different benchmark task, it can win all of them. So it's a very general model that can be fine-tuned to win all of them. Since then, later models can just be primed to do really well on all of them. And then in parallel, of course, similar results with the BERT model out of Google, where it was shown this large pre-training on a lot of text from the internet, and then a bit of fine-tuning on a specific NLP task is enough to have the best performance on that NLP task. So very, very interesting how you have this kind of big general model that can then fine-tune to any of these NLP tasks. Now, the question I was curious about together with some of my collaborators was, well, okay, might these pre-trained transformers be even more general? Maybe generalized beyond language tasks, even though they're trained on language. And so the paper I'm going to chat about here is pre-trained transformers as universal computation engines with Kevin Liu, Aditya Grover, and Igor Mordach. And the idea here is that we're going to train this language model. After it's been trained, in fact, we don't even have to train it. We can just take a pre-trained one. We're going to then fine-tune it on other tasks, but really minimally fine-tune it. We're going to train a very small fraction of the parameters, essentially just the input embedding and the output embedding and the layer norm parameters. What are the other tasks? Instead of language tasks, we'll have bit memory tasks, bit XOR, list operations, MNIST, so image recognition, CFAR, again, image recognition, or even protein prediction problems. So we're training a language and we're going to do all these other things by just changing the input embedding, output layer, just 2 linear layers, that's it, and the layer norm parameters. Here's what we get. We compare in blue what I just described, a frozen pre-trained transformer. We're just training input, output, and layer norm. And then in yellow, when you fully train that same transformer, and we see the blue is pretty much as good as yellow, meaning that fully train that entire transformer on that specific task does not do better than using the pre-trained frozen transformer. So somehow when we train on language, we learn something very general that we don't improve upon by training on this new task that could be in a different domain. And then we also compare with the LSTM as just kind of a comparison to show that it's not just the frozen part that is interesting, it's also the transformer itself. That architecture has something interesting about it. It doesn't work as well within LSTM. Within another experiment, we have the frozen pre-trained transformer in the first row, but then we have random pre-trained transformer in the second row. We have a bit task pre-trained transformer, third row, and then we have a vision transformer in the fourth row. So 4 different ways of pre-training, then freezing, just learning input-output embeddings on top of it, and then testing on these other tasks. And we see that the frozen pre-trained transformer does best almost across the board, better than random, so it's helpful to pre-train on language. On the vision task, the vision pre-trained transformer does a little bit better, so there's a little bit of help there if you pre-train on the right domain. But it's very, very interesting that these things are, even on the vision domains, quite close. So, in summary, I think in robotics, probably the biggest missing piece compared to what we have in computer vision and natural language processing is this notion of a standard but great pre-trained model that we would just grab, like a BERT model or a GPT model or a pre-trained model on ImageNet for vision, that we can just use to then do a wide range of things. I think the question in robotics is actually a bit more complex because it's not just about passive data, there's interaction with the world. And so I have on this slide summarized the kind of overall picture of how I think maybe we can bring something like that together. And I hope this can be inspiration for some of your future work. And I also hope some of you will challenge this picture and maybe tell me how this picture should be changed. And I'm sure at some point we'll realize it will have to be changed a bit. But I'm hoping this is a great starting point and can inspire your research. Thank you. And feel free to reach out with any questions or suggestions. My email is on this slide.